Hello friends, welcome back to our YouTube channel. If you like this video, please like, share and subscribe. I'll share our videos commanded by our experts, so let's begin.
If you like, please like, share and subscribe. So let's begin our today's topic. Let's begin.
Every second, your mobile device acts as a hardware gateway, filtering a constant stream of external network signals and malicious data packets. Historically, mobile financial fraud relied on traditional binary malware, malicious code that operating systems could easily identify and quarantine. Today, attackers bypass code entirely by utilizing real-time social engineering. Standard antivirus software fails against this vector, because the threat payload exists within a spoken human conversation rather than a static file. To counter this specific conversational fraud, Google unveiled a suite of real-time security updates at Google I/O, forming what functions as an Android sentinel barrier. Systematically analyzing live conversations introduces a severe architectural constraint. It requires heavy computational processing, but maintaining strict user privacy demands zero-trust isolation from cloud servers. This diagram illustrates the edge compute privacy paradox. To guarantee privacy, heavy threat intelligence processing must move out of centralized cloud clusters and shrink down to execute entirely within isolated local hardware. To solve this constraint, Android relies on a bifurcated defense matrix. Here, the local device node splits into two branches, a heuristic AI pipeline on one side and a deterministic OS tracking system on the other. We are going to systematically compare the heuristic approach of AI call scanning against the rigid deterministic logic of screen sharing security. Mastering edge-based security requires understanding that applying the exact right architectural paradigm to a specific attack vector is the only viable way to protect limited local compute resources. Focusing strictly on the left column of this structural layout, we find the first branch of the defense matrix, call scanning via heuristic AI. The core mechanism of this system allows the operating system to actively listen to live phone calls originating from unknown numbers to parse conversational context. The system monitors the conversation for specific trigger phrases, specifically targeting patterns typical of scammers, such as urgent requests for personal PINs or claims of being a bank representative. This diagram visualizes the ingest pipeline, where a raw audio waveform feeds into a natural language processing tokenizer, converting speech into machine-readable data. On newer hardware like the Pixel 9 series, this processing pipeline is executed locally by the Gemini Nano AI model. To maintain ecosystem parity, older hardware executes the exact same pipeline using legacy on-device machine learning models. Notice the strict data boundary drawn around the NLP tokenizer. The packets representing the audio and transcripts are physically incapable of leaving the device. Because of this strict local boundary, no audio or text transcripts are ever sent to, recorded, or stored by Google servers. The technical definition for this entire conversational pipeline is stochastic machine learning prediction. Parsing the ambiguity of human deception requires the immense flexibility of a stochastic model, but that flexibility calculates probabilities constantly, making it a severe drain on local processing power. Due to this high computational cost, the feature relies on opt-in deployment. It remains disabled by default, requiring users to actively turn it on in the Google Phone app settings or during an active call. While heuristic AI is highly effective at identifying human deception, its heavy footprint demands strict local isolation. Conversational security is ultimately a resource management problem. Moving away from the fluid, probabilistic nature of neural networks, we must now transition into a system of strict, rigid structural logic. This logic addresses a secondary threat vector, remote access financial fraud, where attackers convince users to expose their banking apps while sharing their screens. This rigid flowchart illustrates screen share protection. Unlike the call scanner, this system operates entirely without large language models or machine learning. The mechanism at work here is deterministic OS state tracking. Rather than trying to interpret conversational context, the operating system simply monitors the active state of specific applications against a strict set of rules. First, the system checks, is a call active? Is the number unfamiliar? Then it evaluates, is the screen being shared? Is a financial app opening? If all conditions are true, it triggers an immediate alert and block. In practice, the operating system automatically restricts the visibility and execution of payment applications like Google Pay while these specific conditions remain active. This system requires minimal compute overhead and guarantees a 0% false positive rate for its specific triggers. Because this state tracking functions at the deepest layer of the operating system rather than the application layer, malicious actors cannot bypass it by manipulating user app permissions. Unlike parsing conversational speech, mitigating remote access fraud is a deterministic problem. OS-level Boolean logic remains vastly superior to AI when dealing with structurally predictable exploitation routes. Looking at this wide view of digital routing nodes connecting cellular networks, we introduce the concept of origin identity. There is a critical prerequisite flaw shared by both the AI call scanner and the deterministic screen share protection system. Both architectures rely heavily on a single triggering condition. The incoming caller must be classified by the phone as an unknown number. Threat actors routinely bypass this condition by using caller ID spoofing tactics to digitally impersonate known contacts, like family members, tricking the device into trusting the connection. To combat this, Google rolled out a countermeasure within the Android ecosystem, RCS-based fake call detection, integrated directly into the Google Phone app. This illustrates the background handshake. When a known contact initiates a call, a secondary data stream sends an RCS signal behind the scenes. It uses end-to-end encryption to authenticate the origin device in real time, verifying the call is genuinely from that person's hardware. Without this cryptographic baseline, both the AI scanner and the OS state blocker would fail against spoofing. Sophisticated threat architectures are entirely useless without a foundational layer of verified identity. This dynamic collision visualizes the core concept of a multi-layered defense architecture, successfully filtering out distinct, varied threats. Edge compute machine learning tackles the vast unpredictability of human deception, while rigid OS state tracking stops mechanical remote exploits. Stacked vertically, we see the complete Android defense: RCS base layer, OS state middle layer, and Gemini Nano AI top layer. Attacks failing the cryptographic handshake are flagged unknown. The remaining threat splits, monitored simultaneously by the AI audio parser and OS screen tracker. Google secures the mobile ecosystem by layering these distinct architectures to offset the computational limits of mobile hardware. Modern mitigation against advanced social engineering requires deploying distinct architectural paradigms against distinct threat vectors, executing the entire process strictly within the zero-trust boundary of the local edge device. A phone ringing in the dark demands your immediate attention, relying entirely on a psychological sense of urgency. This diagram outlines a standard telecom routing path. When a call comes in, network architecture forces your device to blindly trust the origin metadata. Attackers easily hijack this unverified string, masking their actual overseas node to appear as a trusted local bank. Stopping conversational fraud historically required a blunt and invasive instrument. Systems had to intercept the live audio and route it to external servers to analyze the behavioral patterns of the caller. Engineers faced a rigid paradox. They needed a mechanism to scrutinize live voice audio for complex social engineering tactics without violating the user's end-to-end privacy constraints. Google's recent architectural updates to the Android operating system sidestep this paradox entirely. They engineered an opt-in, real-time scam detection system that abandons cloud analysis. It relies exclusively on Edge AI and cryptographic handshakes executed locally on the device itself. This defense drops the single choke point approach, requiring a sequence of verification steps across the network, the local compute hardware, and the operating system layers. By design, the architecture remains disabled by default. The user must manually activate it within their settings, ensuring strict agency over device telemetry. Executing these checks locally turns the mobile operating system into an active verification engine. The first specific attack vector is origin spoofing. A caller ID claims to be a family member or saved contact, but the voice on the line is an attacker. To counter this at the network layer, Google integrated an RCS-based fake call detection system directly into the native phone application. This schematic details the operational mechanics. When a call arrives from a known contact, the app transmits a background RCS signal over a parallel data track to that specific contact's device. This parallel signal initiates a silent, end-to-end encrypted handshake between the two endpoints. A successful handshake mathematically proves that the device making the call is the exact physical hardware registered to that contact's network identity. This process ignores traditional network metadata entirely, rendering legacy SS7 telecom vulnerabilities completely useless against your saved contacts. RCS authentication neutralizes origin spoofing before you even have the chance to answer the call. The second threat vector involves conversational fraud originating from genuinely unknown but visually legitimate numbers. Analyzing the semantic intent of live speech typically demands massive cloud computing power, which immediately breaks the privacy constraint. The hardware solution lies in advanced neural processing units and highly efficient memory architectures, like those found in the Pixel 9 series. These specifications allow lightweight AI engines, specifically Gemini Nano and legacy machine learning models, to execute complex analysis natively. This cross-section maps the localized data flow. Incoming audio streams are converted into text transcripts, strictly within a secure, volatile partition in the device's memory. A strict containment protocol ensures these transcripted strings cannot breach the localized execution environment to reach the cloud. Audio files and conversational transcripts are never transmitted to Google servers, nor are they stored or recorded on the device. Edge computing severs the historical dependency between real-time security analysis and cloud surveillance. With the audio contained, we have to look at the AI's internal logic. What specific semantic data is Gemini Nano listening for within that local sandbox? The model discards static, easily bypassed block lists. Instead, it performs continuous dynamic intent analysis. Inside the sandbox, the AI parses the transcript for specific behavioral triggers. It looks for engineered urgency, instructions for unauthorized financial routing, or direct requests for personal PINs. As it identifies clusters of these patterns, the system calculates a mathematical fraud confidence score in real time. The moment that score crosses the threshold, the system triggers an immediate, multi-sensory interrupt. The phone instantly projects a visual pop-up warning, sounds a distinct audio tone, and initiates a heavy physical vibration. This jarring response is highly intentional. It shatters the scammer's momentum and gives the victim the psychological clarity needed to hang up the phone. By focusing on behavioral semantics rather than static numbers, Edge AI catches novel, zero-day social engineering tactics that traditional filters miss entirely. The final threat vector bypasses the conversation entirely: remote access exploitation, where users are manipulated into compromising their own device data. To address this, the operating system employs a direct countermeasure known as screen sharing protection. This interface diagram demonstrates the behavioral heuristic. The operating system actively monitors if a user attempts to open a payment app like Google Pay while sharing their screen during a call with an unfamiliar number. Upon detecting this precise overlap, the OS dynamically halts the execution or visibility of the financial application, physically preventing the caller from monitoring secure data. This behavioral block patches a critical vulnerability where the user themselves is weaponized against their own secure credentials. This schematic visualizes how these systems combine into a single architecture stack. Layer 1 independently verifies the caller via RCS cryptography. Layer 2 actively parses spoken semantics via Gemini Nano. Layer 3 halts dangerous operating system behaviors during active unknown calls. By encapsulating these verifications entirely on the handset, Android creates a true localized zero-trust environment. This localized AI framework extends beyond synchronous voice calls. The exact same architecture powers the expanded message safety feature, scanning incoming text messages without routing them to external servers. It continuously parses asynchronous text to flag high-risk investment schemes, crypto fraud, and financial impersonation attempts. This integration establishes a comprehensive multi-vector shield across the broader Android ecosystem. Achieving real-time AI security without compromising strict edge compute privacy constraints is a massive feat of hardware and software engineering. Integrating real-time AI and cryptographic verification directly into the hardware creates a device that actively defends the user throughout every interaction.